Yay!
Yay! All right, so last time we found the magnetic field from a loop of current. So this time we're going to stack a whole bunch of them together, like wrapping a cardboard tube with a whole bunch of coils of wire. And when we do that, we're going to form something called, in physics, we call this a solenoid. And we want to know, in this example, is what is the magnetic field there at the center of the solenoid? Okay, so we already know that the magnetic field from a loop, let's see, what was it? It was mu naught. Let's see, I had it written down here. Mu naught I r squared over 2r squared plus z squared, whoops, to the 3/2. Okay, that's the magnitude of the field from a single loop. Here's the problem. The problem is that's fine if we're talking about a certain loop that's a distance z away from the middle that we're interested in. But there's a whole bunch of loops. There's a particular loop where I'm just right in the middle, right, where z is 0. And then there's some loops where the z is further away. So I'm going to have to, what I'm going to have to do is I'm going to have to integrate over all of those loops. I'm going to have to integrate this expression for all the different distances these loops are from the point I want. Okay, so what I have to have is b is, it's going to be mu naught I r squared, and this is going to be 2r squared plus z squared to 3/2. I'm going to integrate from the left-hand side to the right-hand side, where the distance from the point in the middle is 0, so this is going to be minus L over 2 to plus L over 2. Okay, here's the tricky thing. The tricky thing is what is our little integration variable? Well, I'm integrating along z, right, between those two different things. So I'm going to have a dz. But what I want to know is, for a little bit of distance dz, how many loops in this little bit right here, in this little dz, how many loops does that cover as I go dz? Well, what we can do is we can say that there's sort of a loop density, right? The number of loops divided by the whole length. That's the number of loops per, let's say, meter, right? So if I go a tiny little bit of meter, I just multiply that by the loop density, the number of loops per meter, and then I got it. So that's the little tricky bit that we need to put in. So n is the total number of loops that I have, the total number of windings, and then L is the total length. And so if I multiply that by dz, that tells me how many of those things I've got in my little bit of length dz. Okay, so if I have all that stuff, I'm pretty much ready to go. And almost everything, a lot of that stuff are constants, right? They come out front. So I got this. So I got b is mu naught I r squared, and then I got 2r squared plus z squared to the 3/2. I got an n over L. And then finally, oops, I brought out too much. I brought everything out. I can't bring everything out. Okay, it's mu naught I r squared, and I got my 2. Don't bring out r squared, but z is changing. I can't do that. But I can bring out the L and the n. Make it look just a little bit better, 2L. Okay, so then I have minus L over 2 to plus L over 2. And I got my dz over r squared plus z squared to the 3/2. This integral is starting to seem like an old friend. This thing has popped up, like at least 5 times so far. So let's consider it already solved, and we'll just write down what the answer is. So b is mu naught I r squared n over 2L. And then this integral comes out to be I got my z over r squared, and this is going to be, see, I already memorized it, r squared plus z squared minus L over 2 to plus L over 2. All right, so I'm going to plug this stuff in for z. Now, when I do it, we've done this a couple of times already too. The denominator does not change because I'm going minus and plus, and z is being squared, so that doesn't change. In the numerator, I have plus L over 2 minus a minus L over 2, so that's just L. So I'm going to have a mu naught I r squared n over 2L, and this is going to give me an L, so that's going to cancel, over r squared, that's going to cancel, and I'm going to have r squared plus L squared over 4. Okay, so let's cancel this stuff out. L, r squared, r squared. Let me write this up here. What am I left with? Mu naught I n over 2 square root of r squared plus L squared over 4. This should be it. That's the exact answer for the magnetic field at the center of this thing. Normally, what we're going to say is that L, this is another one of these approximations, it's really handy. What if the length is a whole bunch longer than the radius? So if L is a whole bunch bigger than R, this is a pretty useful approximation. A lot of solenoids that we're going to consider are way longer than they are wide. So if L is a whole bunch bigger than R, the L term dominates, right? So it's going to be the square root of L squared over 4. So it's going to be L over 2. That cancels the 2. And so this just becomes something really simple, mu naught I n over L. That's really simple. And the takeaway is that this is a uniform magnetic field. It's not changing, right? It's just a constant. N, L, I, mu naught, those are all just constants. So the magnetic field there at the center, if it's a long solenoid, then it's a uniform magnetic field everywhere in the solenoid, right? If L is basically infinite, it doesn't matter where you are inside. Every bit looks like every other bit. So this is a really useful form for the magnetic field. If you want to create a magnetic field that does not die off with distance, this is how you do it. And if you want a stronger magnetic field, you just have more windings, right? Increase the winding density, the N over L, and you can get a stronger and stronger magnetic field. In practice, this is how you create really, really strong uniform magnetic fields, like in MRI machines, is you have these big solenoids carrying a lot of current. Okay, really, really neat.